Hi everybody, welcome to another video in linear algebra, section 2.4, partition matrices. From previous section, we regard a matrix as a list of column vectors. So pretty much we divide a matrix into columns, or we call the column vector. And this is one way to partition a matrix into blocks, in this case, block of vectors. Now, let's just look at the example. Instead, let A be partitioned into 4 blocks, and the first block, second, third, and fourth is like that. So we divide into 4 blocks. The first one is that. The second, and then that and that. So we divide into blocks. Essentially, we divide the matrix into 2 by 2 blocks. See, 2 rows, 2 columns. So in blocks, it's going to be 2 by 2. And it is like that. And then we say, can we do any operation with that? Well, in this section, certainly, we can. If matrices A and B are the same size and are partitioned in exactly the same way, then we can add or subtract or multiply by a constant. It could be easy. Addition and scalar multiplication should be easy. Just give you a very simple example. I'm just going to write this here. So we have 1, 2, 3, 4, 5, 6. A matrix like this. And of course, in order to add or subtract, they have to have the same size. So let's say we just split into 1, 2, and then 1 and 2. So because they have the same dimension, we'll partition the same way. So we just the first block with the first block, the second block with the second block, and then we combine that. Of course, we still just the regular addition and subtraction, or if we multiply the constant to it, it's just the same way. So addition and scalar multiplication is not much into it. The more interesting is where we multiply matrices together, because the dimension will be a little more interesting. Of course, when we multiply, whether it's in block or not, the usual way is we take the row from the first matrix times the column on the second matrix, and that will be the same way. Now, add that into is where we divide into blocks. In that case, the blocks is still multiplied the same way. The row on the first blocks, the blocks on the first row times the blocks on the first column, in the same way. Now the key in the multiplication is that whatever the column partition in A mismatches the row partition in B. Right. Now, before we do that, let's just look at the very simple example. We have this matrix and that matrix. So let's check the dimension. This is 3 rows, 3 columns, and this one 3 rows, 2 columns. We know that the middle's number must match, and then we just multiply. I'm just going to write the matrices first, and then we multiply. AB, A, 1, 2, 4, 4, 5, 8, negative 2, 0, and 4, negative 1, 2, 0, 5, 6, and 2. Right. Now we multiply just like we normally do. Just take the whole row by columns. First row, first column. Right, I'm just going to do for the first one row, say, then the column. Negative 1, 0, and 24. Negative 1 and 24, that's 23. then row times column, 2, 5, and 8. 2 and 5 and 8, that's 15. And then row times column, -4, 0, and 48, -4 and 48. 8, 25, and 16. 8, 25, and 16. 8, 25, 33, 16, 49. You know, I'm going to check with the calculator, so I'm just going to write that. -2 times -1, 2, 0, and 24, so that will be 26. By the way, we will just do one problem, but in a lot of different ways, so I'm not worried too much about the answer. -4, -4, 0, and 8. -4, -4, and 8. Right. Let's just make sure we just use the calculator here. And 3 by 2. Two, 10, and 8, because that's 20. Right. 2, 10, 8. Right. Of course, just multiplication. Simple. Now, what if we divide the matrix B into a block like that? Right. So I'm just going to keep this on top. Now I'm going to write the matrix A, B again as a product. Now we know that we have to divide B into, and that is a 2 by 2 blocks. So I'm just going to group this into blocks. Right. In that case, if we write the block, this matrix is going by blocks. It's going to be 2 rows of blocks and 2 columns of blocks. Right. If this is the case, we have to partition the matrix AB similar to what we have here. Somehow we can multiply. Let's look at the rule again. The column partition of the first matrix must match the row partition of the second matrix. So what we have here is this matrix. We divide the rows by 2 rows and 1 row. So we have 2 rows and 1 row. So if we're going to divide at this, we have to divide the columns into 2 columns and 1. So again, for matrix B, we divide that into 2 and 1, and then the columns we have to divide into 2 and 1 to match with that. Of course, and then we can just divide this into row, but that's different story. At least we're just going to have to divide like that. Right. So here I'm just saying I'm going to have a block like that, and I have the block like that. Once again, in columns 2 and 1, in rows 2 and 1. So in this case, I have 1 row of blocks by 2 columns of block, and once again the middle numbers must match. And when we multiply this in terms of blocks, we're going to have 1 by 2, right? 1 row of blocks and 2 columns, so we have to have 2 in terms of blocks. Right, now let's write the result. Rows times column, right? So we only have 1 row of blocks here, but there's that 2 columns of blocks, so let's focus on the first one first, like that. Now, rows times column, first with the first, second with the second, and then we add them. So I'm going to write 1, 2, 4, 5, -2 and 0. The first with the first, and then add second on the block, and then 6. Of course, you can write this as the matrix notation too. I mean, this would be the matrix notation, but to write in a block like this, it's easy to visualize. But in reality, this is going to be a matrix, and that will be a matrix. Okay, so that's the first one. Give us this one, and then we have the second row. Just going to say that go over that on the second row, right? Now, row times column in blocks, the first with the first, second with the second. Of course, if you want just the notation of the matrix, this is fine. And then 2 and 5. And then plus second, and then 2. That gives us this entry here. Right. Now, we multiply this together. I'm just going to put in the calculator, so we just write the result. First, I'm going to write this. Three rows, 2 columns. Two rows, 1 column. And then plus 3 rows, 1 column. Right. Of course, this multiplied by 6, so everything multiplied by 6. But I'm just going to say, what if we just have the 1 by 1 matrix? Can we enter like that? Yes, we can. So when we do that, the first part we have is 23, 44, and 26. And then the second one will be, I just copy this because ultimately I'm just going to replace, instead of -1 and 0, I'll replace 2 and 5. And then I replace 2 here. And we have 20, 49, and 4. And you see, this is what we have on the first part of the example, 23, 20, 44, 49, 26, and 4. Right, so when we partition, divide the second matrix into rows, but have to match with the columns, the way you divide the columns in the first matrix. Right, now, of course, here if we want to check the dimension, we can just like say 2 by 3, I think I write pencil. And keep the 3 rows, 2 column, 2 row, 1 column. So multiply that will be 3 and 1. And that multiply also 3 by 1, 1 by 1, so 3 by 1. Yeah, so suddenly you can combine these matrices together. Right. Now, let's do multiply A and B again, but this time matrix B is partitioned into that. Just going to write A and B, right? So A, 1, 2, 4, 4, 5, 8, -2, 0, and 4. And B, this time we only divide this in 2. 2 rows of 2 rows, a block of 2 rows in 1 column. Right, now if we divide the rows into 2 and 1, then the first one we have to divide the columns into 2 and 1. So it's going to be 2, the columns are going to have 2 elements in the columns and 1 element into a column. In that case I have again 1 row, 2 columns. Of course we can divide this into row if we want to, but now let's just say that we have to match the middle, of course, and then when we multiply this we just have the 1 by 1, so when we multiply this we just have 1 block. Right, so and then the term block first with first, second with second, and then we add them. So first block 1, 2, 4, 5, -2 and 0 times that. And then plus second times the second in terms of blocks. Now I check the dimension, 3 rows, 2 columns, 2 rows, 2 columns. When you multiply you have a 3 by 2. so that's one's good. And this is 3 row 1 column, and then 1 row 2 columns. We have 3 by 2. Because 3 by 2 plus 3 by 2 is going to end up with a 3 by 2. It's going to be that. So we need to do, I'm just going to put in a calculator. Let's start from the beginning. 3 by 2. Of course, we know the answer already. It's going to be the same thing here, but just make sure that we do have it. One row, 2 columns of 6 and 2. Of course, we have the same thing. Just one block. Right. Now let's look at this example. Remember, we have, since we partition B into 2 by 1 block, when the first one we have to have the 2 here, so the number of columns in blocks have to be 2. But we cannot just divide any way. Here I have wrote out the same problem, but I say once again we divide this into blocks of 2 and 1, so 2 rows of blocks, 1. Now, instead of divide that, I divide into the columns. Once again, if you check the dimension, 1 row, 2 columns, perfectly fine, right? However, when we multiply first with the first, now we check the dimension, 3 row 1 column, and this is 2 by 2, so that doesn't work, right? We cannot multiply that. The reason being, remember, when we divide into rows, 2 and 1, this is 1 column of 1 and then the column of 2, so it doesn't work. So when we divide them, we have to, let's say, divide into rows into 2 and 1, 2 rows and 1, and then we have to have 2 columns and 1 have to be in the same order, like that. This is 2 row and 1 row, 1 column and 2 columns, they do not match. 2 and 1, 2 and 1 have to match like that. Now, here also I have another example here. This is for that example. We divide into 2 by 2 here. So most importantly, we just need to see how we divide the rows in the second matrix, 2 and 1. So we have to match in terms of column, 2 and 1. So that match. As long as it matches like that, you can just divide the row here. It doesn't affect the problem. But most importantly, again, 2 columns, 1 column, 2 rows, 1 row. So the way we divide, once again, to partition, the row in the second matrix and the column in the first matrix must match. And that is, of course, how we multiply. The middle numbers must match. The rows in the second matrix have to have the same partition as the column of the first matrix. Right. So for that, instead of divide into 1 and 2, I divide that into 2 and 2. So this is 2 by 2 and 2 by 2. When we multiply, we have this. Of course, the answer is still that. Right. Next, we have A times B. Once again, I'm going to write A and B as a product. 1, 2, 4, 4, 5, 8, negative 2, 0, and 4. And then B. negative 1 and 2, 0 and 5, 6 and 2. Now we divide this into column. 1, 2, so 3 columns each. Now, if we divide the columns in the first matrix, the partition have to match with the row of the second matrix. In that case, we have to divide into this. So if we want to write it out again, this is going to be 1 by 3, 1 row, 3 columns of blocks, 3 rows of block by 1. So it's going to have the first one, 1 for negative 2, first with the first, plus second with the second, plus third and the third. When we add all of this together into one big matrix, the answer is going to be the same as this. Right. So once again, the partition in rows of the second matrix have to match the partition in columns of the first matrix. But in this particular, we have this theorem, is that if we divide the matrix A into columns and then matrix B into rows, and then we're just going to write like that. Right. Once again, the first matrix divide partition into columns. The second matrix partition into rows. Those have to match. Yeah, we have to have the matching between, once again, the row on the second matrix, the partition of rows on the second matrix, and the column on the first matrix. Right, now it's more interesting example. Show that block this identity matrix, 0 matrix, A matrix, and I. Suppose all that have the same dimension. Suppose I, 0, A, and I have the same dimension. Find the inverse of that. So, just going to write that matrix now. The nice thing about the inverse matrix, I'm just going to, the identity matrix, I'm just going to draw a very big, let's say 5 by 5. This is a 5 by 5 identity matrix. If we divide into blocks, that is a I2, that is I3, also identity matrix. Right, so what we're trying to find is so that this is invertible, and then we find the inverse. So if it is invertible, then we should have the matrix. Let's say we don't know what it is, because we just say hey, it's going to be B, C, D, and E. We don't know what it is. Now let's just multiply it out in terms of blocks. Row times column, I times B, so I just say IB plus 0D. And then IC plus 0E, AB plus ID, and AC plus IE. Now, if they are inverse of each other, this has to be equal to the identity matrix, meaning that we're going to have the identity matrix. If this is the inverse, then the products of those two matrices must be the identity matrix. Of course, the identity matrix, when we partition it into the identity matrix on the diagonal and 0 everywhere else. Now we're going to match the first block with the first block, the second with the second, third with the third, and fourth with the fourth. And then we have the matrix B, C, D, E. Right. So from here, we will have I, B, I times B, identity times B is still B. Oh, just right. I, B plus 0, D is equal to I, C plus 0, E equal to 0. AB plus ID equal to 0. And AC plus IE equal to identity. Right. Now let's simplify this. It will simplify a lot. 0 times D, because 0 times anything is 0. Anything times identity is identity. So we have B is equal to I. Again, identity, anything times identity is itself. So I times C is going to be C. And 0 times C is 0. So we have C equal to 0. So B is identity, C is 0. Next, A times B. Right. B is identity matrix. I'll just write AB equal to D plus ID equal to 0. So I move D to the other side. I'll just say and AC plus IE equal to identity. Right. So already we have B is identity and C is 0. B is identity, so here B is identity. Anything times identity is itself. Equal to 0. So here we have D is equal to negative A. And here C is equal to 0. So C is equal to 0. So that one go to 0. And identity times E is still identity, still E. So E is identity. E times I is E. So we have E equal to identity matrix. And put that together, the matrix that we're trying to find, B, C, D, E. B is identity, C is 0, D is negative A, and E is identity. Of course, we can check. I0, AI. Now we have what we found is the identity. I mean the inverse. Row times column. So we have I, and then row times column. A, negative A, 0, and I. Yeah, of course we should check the other side as well, but it's going to be the same thing. So quickly, I0, negative AI, I0, AI, row times column, row times column, negative A plus A, 0, and I. Yeah. So that is the inverse of the blocks matrix. Right. Here we have another example here. Let A be partitioned to A11, A12. So it is a 2 by 2 blocks essentially. So do the same thing. A11, A12, 0, A22. I suppose that the dimension will match. I mean into the dimension of the B, C, D, E, and I of the dimension will match into the multiplication. Right, now we don't know what will be the inverse. So once again, we try to show that this is invertible, and we try to find the inverse of this. So we don't know what it is. Just going to say this is going to be a matrix in blocks B, C, D, E. Once again, we multiply it out. A11 row times column B, A12 D, and then A12, A11 C, A12 E. Of course, you can call this B11, B12, B21, and B22, but too many subscript. Besides just 2 by 2, we're just going to say B, C, D, E. That's just fine. So times B plus A22D. And also, when we multiply, make sure this is a block, so do not switch the order of this. So IB and then I and then 0D. Don't change the order like BI, even though in this case that it should work, but let's maintain the order. The first matrix, like A11 times B, A12 times D, do not switch the order of this matrix. 0B, A22D, 0C plus A22E. Once again, if we want this to be invertible of each other, the result have to be the identity matrix, a block. And then we just match first with first and then so on. So we have this system A11B, A12D for I, A11C, A12E have to be equal to 0. 0B and A22D, so that's just A22D equal to 0. And 0 times C is 0, so we have A22E, this one equal to identity. Right. Now on this one, in order to have 0, okay, just look at this one first. This one, obviously A22 times E is equal identity, so meaning E is going to be equal what? A22 inverse. Because the product is identity, they must be inverse of each other. Of course, two matrices times together equal to 0 doesn't mean one of them can be 0. This does not imply that D equal to 0. However, we can choose D to be 0. Like I said, this is not a unique solution. The product equal to 0 doesn't guarantee one of them has to be 0. We talked about this earlier. So in this case, what we do, it does not imply, but we can choose. If we choose D to be 0, things will be a lot easier. That certainly satisfies. And that will be 0. Okay, so this is what we choose, D to be 0, so things will be simplified a lot. Right, now D equal to 0, and that implies D 0 times A12 0, so we have A11B equal to identity, so B must be inverse of A11. Right, and finally, what we have B, we have D, we have E. Now just need to solve for C. Right, substitute what we have. A11, 1. C, that's what we don't know. A12, just leave like that. And then E is A22 inverse. Yeah, I'm going to just use that. And then equal to 0. Now we solve for C, so move that to the other side. A11C equal to negative A12 A22 inverse. And then if we solve for C, multiply the A11 inverse in front of it. So we have C equal to negative A11 inverse. Yeah, multiply A11 inverse on both sides. A11 and A11 inverse cancel out because that identity. And then A12 A22 inverse. Put all of that together. So we have A11 A12 0 A22, and then the matrix that inverse of this is going to be B, C, D. This is B, A11 inverse C will be that. And then D and E. And I'll check real quick. That will be identity 0, so that's good. Now that will be negative A12 and A22 inverse. And A12 and A22 inverse. Subtract, so that will be 0. And then so 0 and 0 and identity. Yeah, so and that check. With this example, change that to B. With this example, we finish section 2.4. As always, thank you for watching and see you in another video in linear algebra.